Hey, I'm Jess. I'm going to introduce our system Otti, which is a compiler for ZK SNARKs that provides support for optimization problems. Obviously, we're going to do this with zero knowledge. That's why we're here. So let's say you need to solve an optimization problem, and you need to prove that you solved it correctly, but your problem involves sensitive data that you don't want to reveal. For example, maybe you're a school and you're admitting a new class of students, and you want to prove that you selected the best or most optimal incoming class, but you don't want to reveal your admissions criteria, and you don't want to leak the data of your potential students. Maybe you have a certain GPA requirement, maybe you have a class cap, maybe you require extracurriculars, whatever. So as a school, you can generate a commitment to your specific admissions criteria. This hides the criteria, but it binds the school system to it so they're consistent in admission. And the school will want to maximize some objective function. This function can select students such that the incoming class is optimal for them. And then the school also wants to ensure their linear constraints. So you can formulate this as a linear optimization problem. So then students apply to the school commits to their data. The school can then prove to everybody that for some set of applicants, those who were granted admission were the best choice for the school given its criteria. And they can do this in zero knowledge without leaking any information about their criteria or about the data of specific students. This is obviously a contrived example, but optimization problems are everywhere, notably resource allocation, scheduling, and neural network training. Otti handles three classes of these optimization problems, which are linear programming, semi-definite programming, and stochastic gradient descent. And it can prove optimality for all of these classes in zero knowledge. So how would we go about doing this? The naive way would be to encode the entire solver as a Boolean or an arithmetic circuit, or some other intermediate representation like rank 1 constraints that can be consumed by a zero knowledge backend. And by solver here, I just mean a program that solves the optimization problem. So our school admissions example is a linear program, and that can be solved with a simplex algorithm. For something like stochastic gradient descent, you can just run the stochastic gradient descent algorithm for many iterations until it converges. And as we saw, these circuits are very big. The features like unbounded loops, features like RAM operations, floating point can cause a huge blow-up in these circuits. For example, if you have a loop that's dependent on runtime data, you have to copy it 1,000,000 times and pick some large upper bound because you don't know how many times it's going to run. The largest linear programming problem that we were able to compile to a circuit in this way only had 5 equations and 5 variables, and it produced an arithmetic circuit with about 1,000,000 multiplication gates, which is obviously pretty far from what we would want in like a real-world instance. So we need to avoid this. So what Otti does is Otti says, well, we don't really care how a prover, like the school in our example, finds the optimal solution. We don't care what solver they use or how efficient it is or what external libraries they use, whatever. All we care about is that the solution is optimal. And it turns out, for many classes of optimization problems, there's a particular structure such that checking that a solution is optimal is much cheaper than computing the solution itself. And what I mean by structure is you can think about sorting. You can check that a list is sorted by just going through and saying, like, is every element bigger than the last element? And is the output and the input contain the same elements? And that's faster than running something like quicksort or merge sort or whatever. So what Otti does is, instead of encoding the entire solver in the proof, the prover just computes the solution and supplies it as non-deterministic input to the proof. And then the proof is just this very small check that the solution is optimal. And this check is very practical. It doesn't need to use loops or RAM or whatever. And so you can use it to solve realistic instances. And it is completely automatable. So to roadmap the rest of the talk for you, I'm going to show you how Otti does this for linear programming. You can see our paper for semi-definite programming and stochastic gradient descent problems, since those techniques are a little bit different. And then I'll give you a high-level description of Otti's pipeline, how you compile a program in Otti, and then I will conclude. So linear programming problems are always of this form. You want to find some vector that maximizes an objective function subject to a matrix of linear constraints. And in optimization theory, this direct translation is just called the primal problem. And any linear optimization problem can be viewed from another perspective. This is called the dual problem. If a primal problem is a maximization problem, the dual problem is a minimization problem, and vice versa. It's basically a turn of the problem. In linear programming, if there's a feasible solution to a bounded problem, the corresponding problem also has a feasible solution. Both problems have an optimal solution, and the optimal primal and dual solutions produce the same objective value. And this is called strong duality. Because of strong duality, we can create a very short certificate to check the optimality of our solution. So what it does is you can imagine, okay, if we're given solutions to our primal and dual problems, x star and y star, just dropped from the sky, all we need to check is that x is indeed a solution to the primal problem, y is indeed a solution to the dual problem, and that strong duality holds. Their objective values are the same. And then that implies that the solutions are optimal. And this is great because it doesn't require any loops, it doesn't require RAM, it doesn't require external libraries, and it can be encoded as a much, much smaller arithmetic circuit than the entire solver can. And since the circuit is so small, it is finally practical to prove optimization problems in zero knowledge. How practical? Here are the results of running Otti on a sequence of problems in the netlib linear programming library, which is a benchmarking library that they use to benchmark linear optimization solvers. And for most of these instances, Otti produces proofs under 50 kilobytes. The biggest instance we were able to compile over here on the far side of the slide had 400 equations and 2,700 variables, and it only produced a proof of 81 kilobytes. And for comparison, the proof that I talked about before with 5 variables and 5 constraints also produced a proof of that size. So now we can, for the same cost, we can get 400 equations and 2,700 variables. So let's talk about the compilation process. First, you input an optimization problem. Let's say this is a linear primal problem. The prover uses any solver it wants to find the solution. For example, in the linear programming case, this might be simplex. And as far as Otti is concerned, this solver is a black box. It can use any optimizations, you can use it on any hardware, whatever you want. And it produces our solutions to our primal and dual problems. Otti then can automatically generate the certificate for this problem and compile it from C to rank 1 constraints. It uses SRC to do this, which is a circuit compiler. And then it uses the Spartan proof system to generate a ZK SNARK for the certificate. Prover can send this proof to the verifier along with the primal and dual solutions. The verifier then uses Spartan to check the proof, and it can either accept or reject. And if it accepts the proof, it can be sure that the solution it has received is the optimal solution to the problem, and no information has been leaked. To zoom in onto the verifier's view for a second, here's what the certificate over here on the far side of the slide actually looks like to the verifier. The verifier gets a satisfying solution to the optimization problem. In our school example, this might represent a list of admitted students. The dual solution, Y, is also provided. It can be provided as a public input or as a private witness to the problem, depending on your application. The linear constraints of the problem, A, B, C. In our school example, this is like the admissions criteria and like the student's data, is hidden behind the commitment. So the verifier learns the structure of the problem, but it doesn't learn any of the data. It learns how big it is, what the certificate looks like, but all the data is hidden. So, as I said before, I'm not going to cover semi-definite programming or stochastic gradient descent. You can see the paper for that, but here is a quick view of how awesome our tool is for it. We ran it on real-world data sets, also used to benchmark, semi-definite programming solvers, etc. We prove full training for perceptrons. And semi-definite programming, we prove stuff on topology design, control systems engineering, etc. There's been previous work done on like inference proofs for machine learning and on training of like select iterations. But as far as I know, this is the first time we've been able to prove full training of realistic ML models in zero knowledge. And it's only 80 kilobytes, which is pretty cool. Otti has some limitations. It has some areas for improvement. We still have an upper size limit. It's still hard to create proofs for very big optimization instances. I think we topped out at about 3,000 variables for linear programming, and stochastic gradient descent topped out at data sets of about 200 features. The bottleneck is not actually proving, but it's the encoding of the problem as rank 1 constraints, which takes a lot of time and memory. And you could imagine outsourcing that compilation to some trusted third party that will compile it for you ahead of time, and then you'll do your prover verifier protocol separately. But there are situations you wouldn't want to trust a third party. So it's still sort of a limitation. Problems have to have a specific structure. like semi-definite programming problems, need to have certain feasibility requirements to satisfy strong duality. Stochastic gradient descent problems have convergence requirements they have to satisfy. And there's an overhead as compared to solvers that don't produce proofs, obviously. It takes longer to produce a proof, even if the proof is small. But Otti is still pretty good. It uses non-determinism pretty aggressively and effectively to reduce proof sizes. It automates away all the optimization math, all the zero-knowledge math, the conversions between tools you have to do. And it generates proofs of optimality that are practical for real-world applications, and it does this much better than any existing approach. All of our code and our artifact is available online. Please go look at it. Thank you guys for your time.